Hello everyone and welcome to this EasyPower webinar. My name is Paul Stechik. I am president of Northeast Power Systems, one of the co-founders. Today we're going to talk about a real world harmonic filter that we have designed and built here at Northeast Power Systems. We actually built 3 of these such systems, each one rated 75 megavars, 5 stages at 38 kV. We're going to kind of do a deep dive into this harmonic filter system. It's destined for a copper concentrate plant, and we will teach a little bit about what a copper concentrate plant is, the type of loads that exist at those types of facilities, and the type of harmonic filters that we have provided in the past to those types of systems. So today we're going to just introduce who NEPSI is. We're going to provide some pictures of some other large copper concentrate harmonic filter systems that we have built. We're going to talk a little bit about large concentrate plants, the types of loads that exist at those types of facilities, and the ratings of those loads. You will find that they are quite large. And then we will provide an in-depth presentation of the 75 MVAR system that I will then show you during a plant walkthrough at our factory here in Queensbury, New York. So just briefly, NEPSI was established in 1995. We are based in Queensbury, New York, which is just 3 hours north of New York City. Our key products are medium voltage metal enclosed power capacitor banks and harmonic filter banks. We only build metal enclosed systems. I will show you briefly that metal enclosed systems come with all switching, all protection, all control. There are some benefits associated with those. We go to a maximum of 200 kV BIL. We manufacture this equipment at our site here in Queensbury, New York. We build the enclosures here. We design the enclosures here, test, and then ship from this location. We do not build capacitors or breakers or switches or disconnect switches or fuses. These components are purchased outright from the other major OEMs like GE, Cooper Power Systems, ABB, Siemens, and the like. We also produce another product called an MVAR product, and we provide startup services and power system studies. So if you want more information about NEPSI, just go to nepsi.com. It's a very rich website full of all kinds of information, tech notes, videos, and more. So just briefly, what is a metal enclosed harmonic filter system? On the left, we show a metal enclosed system. It comes with all switching, all protection, all control. On the right is also a harmonic filter, but it's an open rack type system. So those types of systems we do not build. They are usually built piecemeal on site. And as such, we feel that the metal enclosed solution, when you consider all engineering and procurement, integration, site preparation, installation, commissioning, maintenance, and liability, we feel that the metal enclosed configuration provides a lower cost of ownership. So I'm not going to go too much into the differences here between metal enclosed and open rack. The key here is from a copper concentrate plant's point of view, the reduced installation procurement time is approximately 70% less when you compare it to an open rack system. This is very important for copper concentrate plants because these facilities are typically very remote and then also in very rugged terrain. They could be up at 10,000 feet or they can be in very far locations. We have a small footprint. Typically metal enclosed systems have about an 80% less footprint when compared to an open rack solution. In a mine environment, you would think that space is not expensive, but in fact is very expensive. Copper concentrate plants are typically often located high up in the mountains, and as such, it's hard to find a piece of flat land to support the large footprint associated with metal with an open rack system. And for that reason, the smaller footprint associated with metal enclosed systems becomes more advantageous. So there are some other key advantages, but I think the first two are the main advantages of the metal enclosed system. So moving on, this is what we show here are 2 metal closed harmonic filter systems. This is for the Climax mine. It's a copper concentrate plant up in Leadville, Colorado. It was at 10,300 feet. And that's one of the key things to consider when designing filter systems for the mine environment is you must derate for altitude. Anything above 1,000 meters must be derated for altitude. So this system was 37 megavars, and it's on 2 different bus bars. That's what you see here, the metal closed systems. This system is the Morenci mine. It's in Morenci, Arizona. We sold 2 here at this location. Because of the hot environment, the customer wanted white enclosures for radiation purposes. So these are 11 megavars. Since the altitude was not greater than 1,000 meters, the BIL level was kept at 95 kV. This is a Red Chris mine up in British Columbia, 24.9 kV, 23 megavars, 5 stages. And then finally, this is Carmen del Coy, a copper mine located in Chile. And this system here is rated 33.68 megavars. I see gray enclosures here. And anyways, it was rated 13.8 kV and 125 kV BIL. So large copper concentrate plants, one of the key points here with this slide is the copper ore is taken out of the ground at some locations, typically an open pit mine, and it's done with electric shovels. Those electric shovels can have drive systems that are on the order of 3.5 megawatts. There's also these trucks will then transport the copper ore to a holding location where it would then be transported to a grinding mill through these overland conveyors. And these overland conveyors can also be equipped with multiple drive systems. And these are typically VFD type drive systems that have ratings up to 3.8 megawatts. At the grinding mill, you will find both sag and ball mills. The sag mills can get quite large, on the order of 40 feet in diameter. And also ball mills are also very large. So these systems can get as high as 28 megawatts. And then finally, there's typically a lot of slurry pumps for moving the copper concentrate material around the plant into the flotation process where they obtain the copper through the flotation process. So a typical copper concentrate plant will, on a daily basis, a large concentrate plant would have a throughput of about 120,000 tons of copper ore daily. And from that, they achieve about 1% in copper. In fact, it's even less than 1% in copper typically. So there is a lot of material handling here. You can notice that it is nonlinear type harmonic drive load throughout the plant. And that's the key here, and that is why it is very typical that large harmonic filter systems are required for these types of plants. The gearless drive motors sometimes can be cycle converters, and cycle converters will have a harmonic output that varies with the speed of the mill itself. So if the mill drive slows down, the harmonic output changes, and therefore it basically renders the notch filter unusable, and it is most often high pass and C high pass type filters that are used. So the system that we are supplying into for this project, it had a total plant load of 427 MVA, and it consisted of 3 primary bus bars here. These are 34.5 kV bus bars, and it was fed by 3 150 MVA transformers that are tied together through these tie breakers. You can see here there are sag and ball mills located on each of these 3 main bus bars, and hanging off of these 3 main bus bars are the harmonic filter systems. So each of these harmonic filter systems are rated 75 megavars. They are automatic type harmonic filters, and they consist of C high pass and high pass type harmonic filters. so each stage being 15 megavars. So a 427 MVA plant, it's a very large plant. It has a VAR requirement in the order of 235 megavars without filters. So we had a requirement for 3 75 megavar harmonic filters on this system. It brought the system to a unity power factor, or near unity power factor. The mine was looking to achieve a 0.98 to 1.0 power factor, and also to maintain IEEE 519 compliance at the point of common coupling. And during switching operations of harmonic filters, typically it's typical that the voltage variation at the main bus bars here is limited to a 3% voltage change for each switching operation. So typical performance requirements for the large concentrate plant is to maintain near unity power factor, to adhere to IEEE 519 limits, to limit the voltage fluctuation due to switching operations of a harmonic filter to 3%, to dampen parallel resonances caused by filters, cables, and lines. And you need to do that because most often you have these interharmonics that are of concern, and we cannot excite resonance at those locations. The harmonic filter should avoid fundamental losses, since we are talking about high pass damped type harmonic filters that have the high pass resistors built into them. It is important that the fundamental losses be considered, and this is especially true for the lower order harmonic filters, the second, third harmonic filters. For instance, if a high pass filter is being used, it's important that the fundamental losses be considered. In the design, we are looking to reduce the number of spare parts. We typically look to use a common capacitor across the board, and to use as many common components as possible, so that the mine can reduce their spare parts inventory on site. The mines are looking for a reliability of 99.5% and greater. The cost associated with a shutdown of the filter system can be on the order of millions of dollars a day. This is especially true if the mine cannot operate without a harmonic filter. So a harmonic filter that is of very high reliability is what is being looked for in these type of applications. There are typically some integration requirements in these harmonic filters. The mine operator is typically looking for integration with their DCS system, either through SCADA or through some type of 61850 protocol. Sometimes there might be Profibus with the PLC system located within the control panel. We typically would see dual and redundant communication systems where we are working through a 6185 protection network, and then also working through the process network. And these systems are typically redundant communication type networks. So from an environmental standpoint, of course, the mine is very dusty, and dust is always one of the chief concerns in mine applications. Many mines are located at high altitudes, so derating is very often a area of concern. It's important that the equipment be derated for both ampacity and also for insulation level. Some areas we can have humidity as another concern, and again, reliability, we're looking at 99.5% or more. And we're looking for that. One of the reasons is it's a very remote locations. So, okay, so before we go on to the plant tour, I wanted to review the drawing packages with you. You can see here that we have 62 drawings in this drawing package, so we can't go through all of it, but we typically have a very extensive drawing package. But we will review the three-line diagram, the ratings, and how the system is typically laid out, at least from a three-line standpoint, and then I'll give you a quick overview of the equipment itself. First of all, let's just go through the ratings of the system. This is the key ratings of the equipment here. Hopefully you can see this. Let me expand How's that? Okay, so we have 3rd, 5th, 7th, 11th, and 13th harmonic filters. And you can see here on the right side the types of filters they are. We have a C high pass and then 4 high pass filters. So they're all high pass filters. And as previously mentioned, we're trying to get rid of parallel resonance within the plant from cable capacitance, and also what you would typically get with notch filters if we were to provide multi-tuned notch filters in a plant. We have parallel resonances between those tuning points, and such a filter would not work in a copper concentrate plant because of the inner harmonics that typically exist. You can see here the KVAR outputs are all around 15 megavars each, 14,860 kVAR, so nearly 15 megavars. Fundamental amps, since they're all near 15 megavars, are all in the area of 250 amps. You can see that we calculate what the expected harmonic current, what the expected 60 hertz current is at 10% over voltage. It's important that the rating of the equipment be designed to withstand that 10% over voltage condition at all times as a continuous operating point. And here you can see the RMS harmonic current, and this is the summation of the harmonic currents within the bank, each branch, what we could expect or what the design values are for that filter branch, and then we calculate the total RMS current. So zooming back out here, on this page we have 2 filter branches. We have an incoming filter branch 1, which is stage 1. It's a 3rd harmonic filter. We have filter branch 2. If I flip to the next page, you can see filter branch 3, filter branch 4, filter branch 5. So this is a 3-line diagram, and it lays out the primary key component details of the harmonic filter, the major power components, how they're tied together. You can see here that the capacitor itself, the capacitor bank itself, is tied in a split Y, split ungrounded Y format with a CT and a neutral. Very common for copper concentrate plants. So we're going to start at the beginning of the 3-line diagram, work our way through it, and then show some other drawings. So on the incoming, we have power cables that come in. In this particular case, the power cables are coming in through the roof of the enclosure, through a cable gland plate. We put a set of CTs around those cables, come into a shortening block, and we have an REA 101 relay. This is part of the ultra-fast earthing switch that is provided by ABB. So we are doing arc flash mitigation using the ABB UFIS system. And the benefit of this system is it can eliminate an arc within this filter enclosure within 4 milliseconds. So any damage that could occur due to a flashover within the equipment is quickly minimized to almost just dust within the equipment. Usually the failed component can be replaced. We replace the earthing switches and put the system back in operation. So a very, very quick system. We have a tech note on our website about the ABB ultra-fast earthing switch, and it's something that's worth looking into. Not only does it protect the personnel who are operating the equipment from arc flash, it also protects the equipment from arc flash. Here you can see the ultra-fast earthing switch. These are the primary switching units. When there is a fault within the system, we have optical lenses that will pick up that arc flash event. Those optical lenses transmit a signal to the REA 101 relay, which then goes to a QRU 100 device that will send a trip signal to the ultra-fast earthing switch, or the primary switching units as they would be called. And these are very fast acting grounding switches. Basically, we are taking arc that is through air and transferring it into a bolted fault. And that bolted fault will eliminate the heat and pressure buildup within the enclosure and minimize the damage. Here we show a CPT. In this situation, all control power for the harmonic filter system is taken from this control power transformer. It's a 10 kVA control power transformer. One of the objectives of this project was to minimize the wiring between the customer mine control system, their e-house, and reduce that number of cables down to as close to zero as possible. We have a set of lightning arresters on the main incoming area. From there we feed a collector bus. We call this our collector bus. And you can see here we have 1261 amps of reactive current essentially in this equipment at the incoming. That collector bus will pick up all 5 stages. So 2 stages here and then 3 stages here. This bus is included in our equipment. It comes fully assembled, ready for interconnection. So all of these components, I should say, are assembled into our equipment. It's one of the advantages of the metal closed harmonic filter system, is that it comes with all switching protection and control. There is no putting the equipment up on site. It's done here at our factory. It's tested, it's calibrated, and therefore the commissioning time can be typically less than 1 week from time of receipt of materials at the site. Each stage gets a set of main current transformers here. Again, we feed into shorting blocks as normal, and we feed into a Schweitzer 735 meter relay. I'm going to call it a meter relay because not only does the 735 provide metering functions, it also can provide protection functions. We wire that 735 relay to a 751 Schweitzer relay, which provides the primary control and protection for the bank. So in this case, we're using all Schweitzer technology here. Sometimes we might use other technology such as Siemens or ABB, but in this case, we're using Schweitzer. So 735 power quality meter, we're measuring both voltage and current distortion there. We can monitor each individual harmonic and send trip signals to the 751 relay. The 751 relay is providing the standard protection that you would typically see, 50-51 for both phase and ground fault protection. We use the 4th current input here of the 751 relay to pick up the neutral of the cat bank. And that way we can provide neutral unbalanced current protection for the system. So typically we set this element here within the relay to trip on the operation of a single fuse. We do that because we want to prevent any kind of detuning within the harmonic filter bank. From there we go into a disconnect switch, and from the disconnect switch we provide a circuit breaker. It's a fixed mounted SF6 circuit breaker. So this is the primary switching device. It's what turns the capacitor bank or filter bank on and off to automatically control the plant power factor. The disconnect is there to provide a visible break to allow for maintenance of this branch without having to de-energize the entire system. On the output of the circuit breaker, we split into 2 branches. One is the resistor branch, and then the other is the L and C branch. This is called the aux capacitor here. Again, this is a C high pass filter, so you can see there's aux capacitors here and then the main group here. Essentially what we're doing here is the X of C of the aux capacitors equals the X of L of the reactor, the tuning reactor. This combination tunes to the fundamental, and because the resistor is brought across these 2 elements here, basically at the 60 Hertz level, the fundamental current level, since X of C equals X of L, there's no voltage drop across that resistor, and therefore no losses. We have a set of CTs that monitor those resistors. Here you can see the resistors are 170 kW per phase. Very high kW rating when you kind of think about it, 60 ohms. This provides a damped impedance curve for this filter. In fact, all of these filter branches are very well damped filters to prevent resonance between the tuned frequencies. We use a very simple RMS sensing relay for protection of the resistors. We're just looking at RMS current here, and this is really backup protection for the equipment. but it's very inexpensive backup protection. We have a 4-pole grounding switch. So during maintenance, the 4-pole grounding switch is closed. It helps to ensure that the capacitors are grounded and that the equipment is safe for maintenance purposes. Down here you can see we have the capacitors. We have a total of 30 double bushing capacitors, each rated 660 kVAR at 23 kV. They're arranged in a split Y arrangement, so we have 15 capacitors on each side. If a fuse operates here, an imbalance will occur in the impedance network here and cause current to flow through the CT. And that's how that neutral imbalance scheme works. So if I move on to stage 2, you can see that we have the same arrangement. The difference here is that that there is no aux capacitor in this branch. So during 60 hertz operation, there will be 60 hertz current through here, and there will be a voltage across this resistor. So V squared over R will be the losses within that resistor, and therefore there are fundamental losses in this branch, unlike the second branch, the third tuned branch, excuse me. So we continue with this scheme. We have a 751 relay for each branch, and this 751 relay provides a significant portion of the control of the system and as well as the protection of the system. So I can't get into all the different control protection functions that are typical for these types of systems, but they are quite advanced. I could tell you the 751 relay is a great relay for this type of application. It provides redundant communication and 61850 communication also, and therefore it's a very good relay for this type of project. So moving on, I wanted to quickly show the key interlock system, and we go to sheet 20 here. This is the key interlock system. It's very, very busy, but harmonic filter metal enclosed systems are typically always interlocked, and the basic nature of a key interlock system is to prevent out of sequence operation of the equipment and also inadvertent entry into the equipment. So here we basically have an interlock scheme for each of the branches. This filter system was designed to allow for the disconnecting of any one stage and entry into that stage compartment while having the remainder of the system energized. There are operational constraints with the fact that this is a multi-tune filter system, and that primary operational constraint is that higher order harmonic filters must be de-energized when a lower order tuned filter is de-energized. So the system doesn't allow you to operate on branch 1 here, for instance, and have these energized. Okay, not without doing further system study. There's also a key interlock scheme associated with the upstream device. We don't want to let somebody into the incoming compartment unless the upstream device is open. So that's what you will see, a secondary interlock scheme here. And basically we are forcing the customer to open the upstream breaker before getting entry into the main incoming compartment, as well as the isolation switch compartments of each stage. So finally, I'd like to go to sheet 48, which is an overview of the system, just to give you a feeling of magnitude and size. I would say that this is the largest harmonic filter system that is metal enclosed that was ever built in the world. I would like to see if there's any other system ever that even comes close to this in magnitude of megavars. So it's 75 megavars. You can see here the system is 174 foot long, nearly 53 meters long. So very long. This is how it will look at the substation. This represents 75 megavars, and this is what I will show you during our plant tour. There are 3 such systems being built here at the plant currently, and you will see the first system that is being built. At the end here is a control compartment. We built a hood to allow the operator to stand here. These are not walk-in enclosures. Customer cannot walk into these enclosures. They're not an e-house style piece of equipment. They're not containerized. It's not a containerized solution, but rather a metal closed solution. So without anything further, let me bring you out to the plant. So here I am, Paul Stechik with Northeast Power Systems. I'm standing at the factory in Queensbury, New York, and what you're looking at is by far one of the largest filter banks for a concentrator plant in the world. We are building 3 such systems. If you look down the row here, you can see the filter system on the left and the right. This represents one harmonic filter. It's rated 75 megavars, 150 kV BIL. And it's designed for a copper concentrate plant. It has 5 stages of 15 megavars, and it's tuned at frequencies between the 3rd harmonic and the 13th harmonic. So what you're looking at here is the control panel. And one of the advantages of the metal enclosed harmonic filter system is it comes with all switching, all protection, all control. When you incorporate the control panel into the filter system, what it allows us to do is to completely test the equipment at the site. You can see here we have the panel energized. This is going through final acceptance testing at this point in time. So I'm going to start at the top of the panel, work my way through to explain what you're looking at. So what you're looking at the top here is an ABB UFS system, which is an ultra-fast earthing switch. And that is an arc flash mitigation device. If an arc occurs within this equipment, it will clear the arc within 4 milliseconds. So not only does it protect the people that are working on the equipment, it also protects the equipment. And in a concentrator environment where you can lose millions of dollars a day, it's important that such a system be installed. We have also a touchscreen display here that interfaces with the PLC. This touchscreen display will display all the key parameters of the filter system and will also act as a gateway to the plant DCS system. We have a main 735 meter here, and down below I show 5 more 735 meters. And as previously identified, the 735 meter is a power quality meter. It will monitor each and every harmonic up to the 50th harmonic. It will record P and Q values, and also will display voltage and other very important values for this filter system. So we have one mounted on the main, and we have one mounted on each stage. And this relay, not only does this meter, I guess we would call it power quality meter, not only does it meter, it also provides protection parameters for the 751 relays here. So we have 5 751 meters here. You can see we have touch screens on them. Get them energized. Here, zoom in on this one, Matt. You can see that on the touch screen we can program in the one-line diagram for each branch. We can display the current, the VARs, and the voltage for every branch. These relays, including the 735 meters, have event recorders. They also have monitoring on it. They also have control. The 751 relay forms the heart of the control system here. Just about all protection and control is routed through this device. Therefore, if we lose communication within the equipment, if we lose the PLC within the equipment can still operate. So we're seeking to get near 99.5% reliability on the equipment. That's the key objective of this equipment. I'm going to open the back panel here. You can see in the back panel, I think the key elements here. I'm sorry, let me get on. So we have CT shorting blocks on the right. These CT shorting blocks all come from within the equipment. They do not come from the customer's location. What's I think a key thing to point out here is that from the customer's point of view, they are bringing in phase A, B, and C voltage for voltage signals for the power quality and for the relaying package. And they bring in a ground conductor and then 3 medium voltage power cables. All other communication is through 61850 protocol, or through Siemens using Profibus or Modbus. We have redundant communication systems in the equipment. We have redundant power supplies in the equipment. And we have redundant CPUs. The equipment is able to shut down many different systems and still operate. Over here you'll see there's an onboard UPS system. This UPS system receives power from an internal control power transformer. So the customer is not bringing control power to this equipment. We are providing all control power from a CPT within the equipment. This UPS system here can power the relay package and the control package for up to 8 hours of time. And then here we got a circuit breaker panel which controls the heating and cooling system of the harmonic filter system. And again, that is being powered from CPT within the equipment. We have a fiber optic patch panel here for bringing in the customer fiber optics for communication purposes. So let's come around the front here. Here you can note that we just have a simple air conditioning system. This is to maintain the climate within the control panel. The rest of the equipment is cooled by forced air. We have ventilation louvers at the base of the equipment here. These are changeable while the equipment is energized. If you were to pull the filter off while it's energized, you can see that there's protection to prevent people from entering the equipment and being electrocuted. So, just looking into this compartment, this is the incoming compartment of the harmonic filter system, and key here is at the. I'm going to start at the top since they're up there. We got the arc flash sensors right here. Okay, that's part of the ABB UFA system. Each and every compartment has at least one light sensor. There's about a 3 meter overlap that we use in the sensing of an arc flash event. Here you can see that there's a control power transformer. This is a 10 kVA control power transformer. It's a completely self-protected control power transformer. We have CTs right here. These are the incoming CTs for the 735 relay that monitors the full bank parameters, and the cables will be coming in through the top through a gland plate. So again, this is all 75 megavars are fed from this point, from these connection points. You can see here we have a quirky interlock mounted on the bus bar. The purpose of that is to be mounted in the upstream switchgear, and the basic premise behind this lock here is the upstream switchgear must be locked open to gain access to this compartment. So we have quirky interlocks on the door, and the only way to get into this door is through quirky interlock, which comes from the upstream gear. All right, so proceeding on to the next one here. All right. So we have 5 stages. What you're looking at here is just stage 1. Okay, and the stage 1, okay, is the third tune filter. This is 15 megavars. Each stage is 15 megavars for a total of 75 megavars. So we have a load interrupter switch. The first thing to note here is we have quirky interlocked on the air interrupter switch. We don't want to allow the interrupter switch to operate. So the first key comes from the control panel, where the control panel will shut the equipment down. Okay, that key comes over to this. We put it here. We have spare keys here at this time, and you can operate the air disconnect switch. All right. Let me see here. We have spare keys everywhere. All right, and that's the way you would enter the equipment. And again, this is considered an incoming live compartment. So these doors here will be interlocked with the main breaker. Okay, so what we're looking at basically is switchgear integrated with the harmonic filter system. I'll operate that air disconnect switch again. You can see it operates like that. So this is a non-load break device. Technically you can break load, but they're not rated for capacitor switching. So we are always ensure that the system is disconnected before we allow opening of the disconnect switch. And that's dictated by the key interlock scheme. So the main incoming bus bars are on the back here. And that goes the full length of the equipment, these bus bars in the back. All right, and that'll go for the total of 150 foot there that this equipment is in length, 174 feet, sorry. So this air disconnect switch feeds into the next compartment, which would represent the breaker compartment, or stage 1 breaker compartment. And that is the device that actually operates the breaker. Let me show you that. Alright, so stage 1 breaker, not too exciting. This is a HT4 breaker manufactured by ABB. And again, this is operated by the control and protection system at the control panel. So not a whole lot to see here. This is a fixed mounted breaker. It's not a rollout breaker. 31.5 kA rated, and because this SF6 is very well suited for capacitor bank switching and harmonic filter bank switching. So we enter into the reactor enclosure. And I'm going to open a couple doors just to get some light in here. So what you're looking at here are the iron core reactors. You can see they're quite big. So this one is nearly 6 foot tall. So this is a 15 MVAR iron core reactor. We cannot use air core reactors inside an enclosure. And you can see that these are quite large. So we have these designed with a very significant healthy margin, and we do that for reliability purposes. It's very common that the harmonic current rating of the reactor is equal to the fundamental current rating of the reactor, even when the values are specified much lower. And we do that for reliability purposes. You can see for shipping purposes, we have installed steel channel, welded steel channel. We need to support these reactors for shipping. Once these are arrive on site, these get pulled off, and we just have the insulators here supporting the reactors. So during operation, the iron core reactor is energized. The core of the reactor is energized. It floats at potential. A third tune filter will have roughly 1/9 of the fundamental voltage across the reactor, so it's a much lower voltage across the winding of the reactor during operation. So we get some advantages and some reliability by mounting the reactors up on insulators. We also have some channel up here for shipping purposes. And again, some of these filter systems go to very remote locations, so it's very important that during shipping that the bracing is done very well. These insulators are not designed for shipping, they're designed for holding the reactors after they arrive on site. Maybe you can get in here, Matt, you can see. Again, this is the first stage is a C high pass filter. You can see we have bushings up through the ceiling here. Those bushings up through the ceiling will supply the resistors. And in the first stage, we're looking at 170 kW resistors rated 60 ohms. So we're sending power up to the ceiling. They are harmonic damping resistors, stainless steel grid resistors. So let's proceed on to this. So a C high pass filter, it means it has aux capacitors. And what you're looking at here is the aux capacitor compartment. Okay, and the purpose of these capacitors, okay, is to negate the inductance or reactance, inductive reactance of the reactor, such that at the fundamental frequency, there is no voltage drop across the two components, and therefore there are no losses across the resistor. So X of C equals X of L at 60 Hertz, or if it's 50 Hertz, a 50 Hertz system, and it would short the resistor out at the fundamental frequency, and therefore there would be no fundamental losses. This is a very common design for low tune filters, second, third, and sometimes fifth harmonic filters. a lot of savings can be obtained by using C high pass type harmonic filters. Also want to note that there is a fan here. We use only transformer cooling fans to cool the filter systems. These are by far the most reliable type of fan to use. So moving on to the main capacitor compartment. And this is what really supplies the effective kVAR of the bank. As you can see here, we have shunt capacitors, shunt power capacitors, or 2 bushing capacitors, 150 kV DIL rated, and they're 660 kVAR each. We have fuse clips here that mount here. We don't have the fuses installed for shipping purposes. In fact, we have one installed over here for you to look at. Look at this. You see here, there's a current limiting fuse. You have to use current limiting fuse in metal closed systems. You can't have expulsion gases with an expulsion type, weak link type fuse. Here you'll note that there's a push rod, we call it. It's a blown fuse. It's part of the blown fuse detection system. Not only do we do split Y current detection, but we also do direct fuse sensing, and that's this device here. This feeds a micro switch that's located behind the capacitor down here at ground potential. And I'm not sure if you're able to see that. Yeah, you probably can see it. It's here. This is a dielectric push rod. When I push on this, it activates a micro switch that communicates with the relay package that's in the equipment to identify either a failing fuse or a fuse that has operated. And on medium voltage banks, it's very important to consider fuse failure as a failure mode for your equipment. So all of our filter banks and capacitor banks get this blown fuse detection system. One to detect a blown fuse condition, but another to detect a failing fuse that might be over temperatured. Here you can see we have a ground switch. This is a 4-pole ground switch. Since it's a split Y neutral bank, we had to have a 4-pole ground switch. We ground both the phase conductors and then also the neutral. You can see here, this is the ground switch. It's very easy to operate. That's it. We put viewing windows in all the doors, including the disconnect switch compartment and also in the ground switch compartment to allow viewing of the switch when it operates. So another thing to note here is you can see we're at a section divide here. So this is the end of stage 1, and then we have stage 2. So the equipment is all built from the floor up using C-channel and the seat and structural steel tubing. So everything is lifted from the base of the equipment. This is a typical for an 8-point lift that we have. Maybe you can see the channel on the inside here. You can see here that we have C-channel, it's all channel. And also note the ground bus here. The ground bus will extend through to the next compartment. So we have a continuous ground bus along the equipment that grounds the equipment along this whole length. So the bank has shipped this 75 megaVAR system is shipped with 6 major splits and 15 resistor compartments. That's the equipment in total for the shipment. We figured that it can be put on site in less than a week with an 8-man crew. It can be put onto the pad and fully interconnected within 2 days. And typically, because everything is switched, everything is tested at the factory before it ships, we can commission the equipment in just a couple days after it arrives, or after it's installed. Right, so, you're going to probably have to shut that down. I'm going to climb up to the top, show you what's on top, and then we'll show you the resistor compartment, and we'll be complete with the walkthrough of this equipment. All right, so I'm on top of the equipment after that long climb. What I want to first point out here is we have bushings protruding through the ceiling. And if you recall from the first part of the presentation, there is the resistors on top here. This represents one phase
and this is stage 1, phase A resistors. These are the bushings that come through the roof that connect across the aux capacitor and the reactor in the C high pass filter branch. Just about 50 amps of current flows through these bushings, so they're heavily overrated. One thing to notice is the concentrate plant, and because of dust, we always go up 1 BIL level on the outside of the equipment. So this equipment was 150 kV BIL rated on the inside. On the outside, because of dust, we rate the equipment 200. We're always 1 BIL level up. Also, you can note that we have webbing here on the roof. The webbing here is put in place to receive the high pass filter resistors. And what I'm going to do next is I'm going to bring over to a high pass filter resistor cabinet that will be mounted on top of this, and it will complete the presentation. All right, I lied. We're going to do a couple more things before we get done. Right here is the swing out panel for the filter B. We have an ABC filter system that's being installed at this plant, each being 75 megavars. I want you to look at this wiring here. Okay, a significant amount of wiring. When you have an open air harmonic filter system and you have the control panel and the E-house, this is what goes out to the open rack system. You have CTs, you have PTs, you have the switching device, A and B contacts, you have the open and closed coils of the breaker, you have the charging motor. There is a significant amount of wiring, and you need to do all that at the substation. You have to first run it underground, you have to connect it at the rack, and then somebody has to bug it out and confirm that it's all proper. So this is one of the advantages of the metal closed system, is you eliminate all this by doing it on site. All right, one more thing is worth noting is I'm standing here at the fifth stage of this equipment, which has a reactor that's rated 12.83. The interesting thing here is you saw me at the beginning of the presentation where I was standing on the side of a 6-foot reactor. Here we're looking at something that's merely 3 foot tall, but it does in fact have the same MVAR rating as that first tuned filter. The difference is the fundamental voltage drop across the reactor is much less in the higher tuned filter, and the harmonic frequency doesn't add to the flux density as quickly as a second tuned filter or third tuned filter. So as you go up in frequency, you can expect your iron core reactors to become smaller, even though they're at the same effective MVAR rating at the fundamental. All right, resistors. It's good, right? All right. So I'm standing here at the, this is a second stage high pass filter resistors. There's the stage 2, and the stage 2, just to give you a point of reference, the stage 2 are 50 ohm resistors. This is just one phase. Okay, you can see, you kind of peek into here, these are a grid type resistor. They're stainless steel grid resistors. Each one of these grid resistors is rated 5.25 ohms cold. You can see we have 1, 2, 3, 4, 5, 6, 7, 8. They're all series connected. We series connect these to increase the voltage rating of the resistor. This is very, very important thing to do. Otherwise, you can have flashover during energization of the equipment. Okay, it's important to assume more than just the IR voltage drop across the resistor when designing these. So these resistors here have a rating of 180 kW per phase, 50 ohms. So we're talking about a lot of power here, and that's why the enclosure is not painted. It's a 409 stainless, and this enclosure will get hot. We do not use fans to cool the equipment. It's just natural convection, and that's how we cool the equipment. And this is just one phase, stage 2. The other thing I wanted to note is you can see here that we have the resistors mounted on insulators. These are 200 kV BIL insulators. I've noted on top that that the bushings were 200 kVBIL because they're subjected to the dust of the concentrate plant, and the resistors themselves are also 200 kVBIL. So those bushings will come up through the floor here, and it will connect with these resistors to form the C-high pass filter. That's it.
Okay, this ends our presentation. I will stick around to answer questions. Feel free to ask those questions. And if you are looking for a metal enclosed harmonic filter system or would like to discuss a project with myself, you can contact me at paul.stejek@nepsi.com. And don't forget to go to our website, nepsi.com, for additional information about our product offering. Thank you.